Okay, so this will be a short video, basically just expanding on something we touched on a little bit in the previous video with dimensions and units, and that topic is going to be temperature scales. So what we're going to use in this class is simply the Celsius and Kelvin temperature scales. And the Celsius temperature scale, as many of you probably already know, is related to the Fahrenheit temperature scale in this way. So if I gave you degrees C, um, you multiply that by 1.8, add 32, and that'll give you the degrees Fahrenheit. And you can invert this easily. Subtract 32 and divide by 1.8, and you can do the opposite if I gave you Fahrenheit. Now, the Celsius scale is based on sort of phase transitions at room temperature for water. So it's based on sort of the properties of H2O. All right, so 0 degrees C is where water freezes. Is where water freezes at 1 atmosphere, or at the at mean sea level. And then 100 degrees C, water boils at 1 atmosphere. And the exact reason why I keep specifying a pressure here will become clear to you later on. So if you ever looked at the instructions for cooking rice, you'll see that the times vary as a function of your elevation, and that's related to the fact that water boils at different temperatures at different elevations, i.e. different pressures. Okay, so the Celsius scale is based on this, but the Kelvin scale is based off of a concept of absolute zero. And it increments at the same rate as Celsius. Okay, so it's essentially degrees Celsius just shifted so that 0 Kelvin, again, there's no degree symbol for Kelvin, so 0 Kelvin is absolute zero, which is a sort of absolute zero is the sort of a theoretical point at which all molecular motion stops. Okay, if I had a cylinder of gas and that gas is at temperature T and it has a pressure, if you guys remember, through experiments, the pressure and temperature were related linearly, at least to a good approximation. Okay, and so different gases had different slopes, but the relationship that they were all linear. So this could be nitrogen, for instance, or this could be oxygen. I'm not sure, I'm kind of making this up, but the slopes may differ, but the linear relationship is the same, and they all seemingly cross at some point. That point was marked as absolute zero. So this would constitute a better basis upon which to base our temperature scale than just say the arbitrary properties of water at 1 atmosphere. Okay, so this experiment was actually done. So I have a tank, and I cool or vary the temperature of a certain gas that's captured inside this tank, and I record the pressure. And I notice this linear relationship, and I do it with different gases, and I also notice linear relationships, and I can extrapolate those linear relationships down to a point where they would all cross, and where this pressure would essentially be zero. Okay, and at that point, we'll label that as our new 0 degrees, and that's exactly what they did. So 0 Kelvin is zero, um, is defined as absolute zero based off of similar arguments. Okay, and so the temperature in degrees Kelvin is equal to the temperature degrees C, but just shifted by 273.15. Okay, so the scale is the same, or the change, and as a consequence, a change in temperature in degrees or in Kelvin is equal to a change, is numerically equivalent to a change in temperature in expressed in degrees C. Okay, so for example, say I have an initial temperature of 30 degrees C, and I can convert that into Kelvin, and that's 303.15 Kelvin. And I have a final temperature of 40 degrees C, and I can convert that into Kelvin. Okay, but then if I want to know the difference, if I want to know the change in temperature during this process, which is just going to be TF minus T initial, so the final temperature minus the initial temperature, that's going to be 10 degrees C, but it's also going to be 10 degrees Kelvin. So you can convert temperatures from Celsius to Kelvin, but be careful not to convert temperature differences between Celsius and Kelvin, because 10 degrees Celsius would be what, like, 283 Kelvin. So 283 Kelvin, you could see how this would be a dramatic difference. Like if I thought this was 283 degrees Kelvin change, you follow what I'm saying? So changes in temperature have the same numerical value in these two scales.